All right, in this video, we're going to take a look at another integration method involving trigonometric functions, but in this one, it's going to be almost opposite of what we did in the last video. In our last video, we did U substitution with trig functions. So we took these combinations of trigonometric functions and essentially used a variable substitution to condense things down into power functions. Now, we're going to do almost the opposite thing. We're going to use a trigonometric substitution to expand our functions into something with trig functions so that we can take advantage of that. I'll show off a motivating example, try and explain why we're doing what we're doing, then we'll go through the process and a couple of examples with all these variable substitutions converting back and forth. So let's dive into that right ahead. We're going to remember how we did arc length earlier on in the semester, and our formula for arc length looked like this. It was an integral from a to b of a square root of 1 plus a derivative squared. And so we can say, all right, we need y prime. Well, this is nice. Y prime is just going to be the linear function x. We're going from 0 to 1, so we are looking at the integral from 0 to 1 of the square root of 1 plus x squared. And so we want to play with this integral. What we'll notice is that it's a seemingly small integrand function, but so far it's pretty tricky for us to mess around with. And so we have to try and think of how trig functions might help. So an annoying thing here is that we have this square root and there's a sum. A lot of students want to do something called the freshman dream. It's something that's not true, so I should put a not equals here. This would be nice if we could split this square root up across our plus sign, across our sum, but we can't. If we could, this would just be a 1 plus x and things would be really great, but we're not able to do that. We are able to split things up across products, though. So like a square root of 4x squared is actually the square root of 4 times the square root of x squared, and so we could call this one 2x. So products are good to split up with square roots, sums and differences are not. So what we're going to try and do as our goal is to transform these sums and differences of squares into products. Because if we can transform them into a product of two things multiplied by each other squared, then we can deal with that square root and we're just left with the absolute value of the product. We're going to utilize the Pythagorean identities to do this. We're going to try and use those identities to take sums of trig functions and 1 and convert those into some other trig function. So we should be able to turn sums and differences into products. Then we're going to do a variable substitution, but instead of making u some function of x, what we're going to do is we're going to take all the x's and we're going to replace them with functions of theta. And then we're going to look at the differential, the derivative of x, and we're going to replace that with a big function of theta times a differential of theta. So we're actually going to be adding things into our integral, which is kind of weird. Let's take a look at our example, though, and see what we have going on. What I want us to notice is that this kind of looks like the Pythagorean theorem, almost. If we were to draw a triangle here, we'd say this looks like the hypotenuse of that triangle, the square root of 1 plus x squared. And then we could try and figure out what the other side lengths were. Well, if this is our c, then you could say like the square root of 1 plus x squared equals a squared plus b squared, our other two side lengths. But if you square this, you get 1 plus x squared. And so we can see hopefully pretty easily that a is 1 and b is x. Oops, there we go. Cool. So now what we want to do is to come up with some sort of a trig function that represents x. If you go back to our goal, we're going to say x is some function of theta. We're going to pick a trig function here. So we need to figure out what is x. Or if you want, you could say x over 1. So we're looking at this side length divided by this side length. If we put our angle right here, then we should hopefully see that tangent of theta is equal to x over 1, or x is equal to tangent theta. Dx then is the derivative of that, that's secant squared, d theta. So our variable substitution is going to be this, and we're going to swap out these things. We're going to take x, and we're going to put in tangent theta, and we're going to take dx, and we'll swap that out with a secant squared theta d theta. Our new integral looks like this. 1 plus, not x squared anymore, tangent squared theta. And instead of dx, we have secant squared theta d theta. So again, this is taking the place of dx, and this is taking the place of x. Doesn't it seem kind of counterintuitive because we're making this integral look worse? The whole point, though, is that this stuff underneath our square root here is the Pythagorean identity for the secant squared function. So what we really have is that this is secant squared theta. Our new integral, then, is actually the square root of secant squared theta times secant squared theta d theta. Well, that's secant theta times secant squared theta. That's just secant cubed theta d theta. And this is an integral we did last time. We used a reduction formula for this, but we ended up with secant x tangent x over 2 plus a half natural log secant x plus tangent x. Now, this is a definite integral from 0 to 1. So you could either, oh, I've got x's in here. I need thetas. Whoops. So you could do a couple of things here. You could either go ahead and say, well, if x is equal to 0, then my theta values are going to be like inverse tangents, right? We could solve this for theta. And we could say, well, really these limits of integration then are inverse tangent of 0, which is 0, and inverse tangent of 1, which is pi over 4. And now we've got these limits of integration that we can put in here and evaluate all of this from 0 to pi over 4. Or if you'd like, you can notice that we have a bunch of functions of theta. And all of our functions of theta are trig functions that we can grab right from this triangle. So if you'd like, you could say secant theta is going to be the reciprocal of the cosine function. So we can say that's going to be the square root of 1 plus x squared. Our tangent theta is opposite over adjacent. That's x, all that over 2, plus half natural log of our secant theta, which we said was the square root of 1 plus x squared over the adjacent leg 1 plus x. And we could evaluate this from 0 to 1. Either one is fine. Things work out pretty well then. So I'm not going to actually evaluate this. You can do it, and it's not hard, right? You're just plugging in these values. It's probably easier to evaluate with these x values. Plug in 1 for x, then plug in 0, subtract, everything's done. But what we really want to focus on is how to formalize this idea of this trigonometric substitution. So let's talk about that. We have 6 trigonometric functions, so in theory there are 6 substitutions, but in reality we'll only use 3. We'll notice that we could go back and instead of using, what do we use here, this tangent function, we could go ahead and put our theta, maybe I'll just put it in gray over here, on the other angle, and then what we have is that cotangent theta is equal to x. The only difference is that when you differentiate, you're going to get a negative cosecant squared, and so you're going to have some negative signs with cosecants instead of secants and cotangents instead of tangents. Some of the other little things will get changed, but eventually you're going to track yourself down to the same thing. So what you'll find to be standard is that we pick the 3 functions that have non-negative derivatives. I shouldn't say non-negative, but they don't introduce an opposite sign. So for instance, the derivative of sine is positive cosine. The derivative of cosine is negative sine. So instead of doing a variable substitution where we pick the cosine function and then have a negative floating around that we have to introduce, what we'll notice is that we normally will pick sine, tangent, and secant as our 3 substitution functions. I'm going to draw some triangles for each of these that will hopefully show how we can set these things up. Drawing a right triangle is super important for all of these examples. Let me just copy paste this thing. There's my second one, and here comes my third one. So what we'll do is we'll label all the sides of these triangles based on what we've got. This middle one we've already done. Here's our square root of a squared plus x squared. We'll call this side length x and this one a. It doesn't really matter though, because who cares which of these side lengths is which. But if that's what we're going to do, I'm going to put my angle right here, and then I can see that tangent theta is equal to x over a, which means, maybe I'll write this underneath, and I'll do it in blue. X is equal to a tan theta, and that means that dx is equal to a secant squared theta d theta. In our example, a was 1 because we had a 1 squared in here, but we can have other constants floating around. Now, how do we know to set this up? We've got this sum underneath here, and so we should think the sum of two side lengths squared, that sounds like a hypotenuse. So that's where we can place it. Then for these ones, to figure out which side length is the hypotenuse, we should think about which side length is biggest. We're subtracting some stuff, and so you can see this a squared minus x squared has to be positive because it's under a square root. That means a has to be bigger than x. Well, the hypotenuse is the biggest side length, so let's call that one a. That means x can be whatever other one we want. It really doesn't matter. And then we can put our square root of a squared minus x squared here by the Pythagorean identity. I maybe will go ahead and put theta right here, because then what we'll notice is that sine of theta equals x over a. And so we can do the same kind of thing that we did earlier. X is equal to a sine theta. And that means that dx is equal to a cosine theta d theta. Similarly, in this last one, we can see x is the longest side length because this is the one that we're subtracting stuff from. So either the difference or the thing that we're subtracting has to be smaller than x. Then I need to place a as my other side length. I'll put it here. And I can put my square root of x squared minus a squared right here from the Pythagorean identity. If I put theta right in this bottom corner, then you can see that secant theta equals x over a, because it's the reciprocal of the cosine function, which is the adjacent leg over the hypotenuse. That means that x is equal to a secant theta, and dx is equal to a secant theta tan theta d theta. So this is our guideline. This is our key for setting up these trigonometric substitutions. What you'll notice is that if you put theta in these other angles over here, you're going to end up with, I want to connect that side length again. You're going to end up with, instead of a sine substitution, a cosine one. And instead of a tangent substitution, a cotangent one. And instead of a secant substitution, a cosecant one. So you end up with all the cofunctions. So they end up being the exact same thing. It's typical that we just choose these three. For me, I always choose these ones because it does not introduce new negatives, but do whatever you'd like. Let's take a look at some examples. So again, first thing that I'll do is just draw this triangle. Not a very good one, but oh well. I'm going to look at this square root here, and I've got a sum. That means that this thing, the square root of x squared plus a squared, in this case, x squared plus 4, is my hypotenuse. That means my other side lengths are x and 2. So I need to connect these. I'm going to use a tangent substitution with theta right here. So I can see tangent theta is equal to x over 2, and that means that x is equal to 2 tan theta, and dx equals 2 secant squared theta d theta. So what we're going to do now is take all of our spots where we have x's, and we're going to put 2 tan theta in there. And we're going to take this dx in the numerator and put 2 secant squared theta d theta. So we have an integral of 2 secant squared theta. I'll put the d theta at the very end. And out here we've got x squared. That's 2 tangent theta squared. So I'll say that's 4 tangent squared theta times the square root of 4 tangent squared theta plus 4. Now remember, we want all the magic stuff to happen in here. We want to use a Pythagorean identity to change this sum to a product. So the way that I'm going to do that is to factor. And then that tangent squared theta plus 1 turns into a secant squared. So what we really have under that square root, we have that 4 tangent squared theta in the denominator. Under that square root, what we really have is 4 secant squared theta. And we can actually square root this. This is a product of two perfect squares. So the square root of 4 is 2. The square root of secant squared theta is secant theta. So we have 2 secant squared theta over 4 tangent squared theta times 2 secant theta. And then there's a d theta hanging around way at the very end. At this point, our integral looks still pretty terrible, but let's go ahead and see what we can reduce. I can cancel out a copy of secant. I can cancel out a factor of 2. I'm going to bring out my coefficient of a fourth. Then I've got a secant theta over tan squared theta d theta. And this might be a little bit tricky to see how this is going to work out really nicely. But maybe you can just kind of play with this, put it in terms of sines and cosines, mess around with identities and stuff like that. This kind of feels almost like a trig problem where you have to rewrite this in terms of something else. So maybe I'll write that secant as 1 over cosine theta, and the tangent squared, I'll write it as sine squared theta over cosine squared theta. There are other ways of doing this, but whatever. So we can see that there's going to be some canceling out, and what you're left with is, a cosine theta over sine squared theta d theta, which is really, I'll call this, maybe I'll write it as 1 over sine theta times cosine theta over sine theta. And isn't that cosecant cotangent? And this is the derivative of negative cosecant theta. So what we have is that this is negative 1/4 cosecant theta plus c. Now, we want to switch things back to our original variables. So we got to go back to our triangle and figure out what cosecant theta is. Cosecant theta is the reciprocal of the sine function. So instead of opposite over hypotenuse, it's the hypotenuse over the opposite side. So this is really negative 1/4 times the square root of x squared plus 4 over x plus c. And there we go. Trig substitution. Go ahead and give this one a shot. See if you can set up your triangle, do the substitution, follow through with what's going on. You might notice that it looks a little weird because there's no square root. Well, there really is. This is really the square root of 1 minus x squared cubed. So set things up and see what you can do. We'll use a sine substitution. Hopefully you saw. 1 is the hypotenuse because it's the biggest piece in that little square root thing. And then we can set everything up for the rest of the way, and we get this nice sine substitution, and we've got a Pythagorean theorem down here. So, or a Pythagorean identity, I should say, sorry. So the square root of 1 minus sine squared is really the square root of cosine squared. And then we end up cubing this. Well, the square root of cosine squared is just cosine. Then we have a cosine cubed. Cosine over cosine cubed is 1 over cosine squared theta d theta. Well, and 1 over cosine squared, that's really secant squared. Oh, let me fix that integral sign. And the antiderivative of secant squared is obviously tangent theta plus c. But wait a second. What's tangent theta plus c here? Tangent is our opposite over our hypotenuse, so that is x over 1. This is just x plus c. I don't like that. Oh, silly. That's because tangent is not the opposite over the hypotenuse. Duh. It's the opposite over the adjacent leg. So this is better. X over the square root of 1 minus x squared plus c. Yeah, that feels better. Okay. I was losing my mind there for a second. This one looks a little bit harder. You could notice that maybe we could do some substitutions or something like that to get things set up nicer. I'm going to give a little hint at the very beginning, and I'm going to complete the square underneath here. I'm going to say this is really x plus 2 squared. But if it was x plus 2 squared, that's x squared plus 4x plus 4. And we have a minus 5, meaning it's really minus 9 over x plus 2. What might be easiest is to start off with a u substitution right away and say, well, u is equal to x plus 2 and du is equal to dx. So now we've got the square root of u squared minus 9 over u du. This might be a little bit easier. So go ahead, set up your triangle. Notice that things will be in terms of u's and thetas instead of x's and thetas here. But then when we're finished, we'll put everything back into terms of u's, and then we can put things back in terms of x's if you'd like. Try this one. Make sure you pause the video and give it an honest-to-goodness shot. All right, so likely this is where we're at, right? We do a variable substitution. Since u is the hypotenuse, that means 3 is this leg over here, and then we have our square root. It's nice to put our angle in this position so that we can pick the secant function to be our substitution, because now secant of theta equals u over 3, so that means u equals 3 secant theta. So I've gone ahead and just chucked everything in here, and we can use some Pythagorean identities and start crunching through this. 9 secant squared theta minus 9, well, that's going to be really 9 tangent squared theta, which we'll be able to deal with that square root. Notice we've got these 3 secants and 3 secants, so I'll just call this tangent theta d. That's supposed to be a theta. There we go. So this is really 3 tangent squared theta, d theta. And I don't know the antiderivative of tangent squared right off the bat, but I know I can convert this to secant squareds, and that works out really nicely. So this is really the integral of 3 secant squared theta minus 3 d theta. And then the antiderivative of this secant squared is going to be tangent. And then I have a 3 theta plus c. So tangent theta I know is opposite over adjacent. So this is 3 times that square root divided by 3. So we can call it just that big square root of u squared minus 9. And then theta, we'll have to look at this and say, well, wait a second. Theta is actually going to be an inverse secant of u over 3. So this is now minus 3 inverse secant u over 3 plus c. Lastly, we can go ahead and take this x plus 2 and put it back in place. So I'm running out of room. Maybe I'll put it over here. I've got my square root of x plus 2 squared minus 9. Well, that was x squared plus 4x minus 5. Minus 3 secant inverse of x plus 2 over 3 plus c. That ends up being kind of a tricky way of dealing with things. Notice when we end up with this lone theta here, we can go back and appeal to an inverse trig function based on what our substitution setup is. So that might be a helpful thing to see. Always convert back to our original variables unless it's a definite integral. In that first example, when it was a definite integral, we had the option of just switching our limits of integration over to theta values. And I think in that case we had 0 and pi over 4. Or we could switch our antiderivative back to x's, and then we looked at the integral between 0 and 1. And you can do either one. So always make sure that you put things back in place, and we'll notice that that triangle is super helpful for that. That will give you kind of like a key for converting back and forth. Or go ahead and take your theta and solve it for an inverse trig function if you need to. That's only necessary like in this example where we had just a random 3 constant in our integral, and so we end up with a 3 theta floating around. So keep an eye on that stuff. But that's trig substitution in a nutshell. This ends up being a long integration method because the substitution ends up being kind of bulky and sometimes tricky for students. And once you do that substitution, you end up with another integral that we're going to have to really figure out. So give that a think through, try some examples, and hopefully that goes well for everybody.